So continue our next point of that chapter, that is pharmacokinetic basic consideration. So next term, that is rate constant and the order of reaction. So what is rate? So the rate is the velocity in which a reaction or process will be occur. The rate means it is a velocity in which the process or reaction will be occur, which is called as a rate. Next term, that is order of reaction. On which manner the concentration of the drug which influence the rate of reaction or process, on which manner the rate of the concentration of drug or reactant will be influence the rate of reactions or process, which is called as the order of reaction or order of process. So consider a drug which is changed. Consider a chemical reaction. The drug A which convert into the drug, or chemical compound, the compound which is convert from A to B, or drug A from B. So rate of forward reaction, which is expressed as, so in this for this chemical reaction, the rate of forward reaction which comprises minus dA minus dA by dt. So this negative sign indicates that the concentration of the drug A will be decreases with time as the reaction will be processed. The negative sign indicates the concentration of the this reactant A or drug A will be decreased with time as there will be reaction proceed. The concentration of drug B will be increases and the rate of reaction also be expressed as dB by dt. So in the reaction, the conversion of this A compound or drug A will be converted into the B. So during this reaction, the concentration of the drug A will be decreases with time, and concentration of the drug B will be increased with time. So this negative sign indicates that there is a decrease in concentration of initial compound or drug when we will convert it to the another compound, and another compound the concentration will be their sign will be positive because the concentration will be increases. So rate of reaction, that is dC by dt, is equal to minus kc n inverse. So k will be the rate constant. So k will be the rate constant and n will be the order of reaction. So dC by dt is equal to minus kc n kc inverse. So okay. So k will be the rate constant and n will be the order of reaction. Next will be the zero order reaction, or which is called as a constant rate process. So therefore the order of reaction n will be the zero, and equation becomes for this dC by dt. So we know that the rate of reaction, the equation dC by dt is equal to minus kcn. So for zero order process, the n, that is the order of reaction, will be the zero. So equation becomes this rate process, that is dC by dt is equal to minus k0 into c0. So k0 will be the zero order rate constant in mg per minute. So k0 will be the zero order rate constant in mg per minute. So what is zero order process? So zero order process is defined as the one whose rate which is independent upon the concentration of the drug undergoing the reaction. The rate of reaction cannot be increased further by increasing concentration of reactant. So what is zero order? So zero order process, the one which rate एखाद्या प्रोसेसचा रेट which is independent upon the concentration of drug undergoing the reaction. म्हणजे किती आपण एखाद्या ड्रगचं कॉन्सन्ट्रेशन इन्क्रीज केलं तरी काय रेट ऑफ रिएक्शन विल बी फर्दर नॉट चेंज, किंवा रेट ऑफ रिएक्शन विल बी कॉन्स्टंट. So which is called as a zero order process. So which is depend as one whose rate it is independent of the concentration of drug undergoing the reaction, that is rate of reaction cannot be increased by further increase in concentration of reactant. So they are converted. So this C is equal to C0 minus A0 into T. So finally the equation the C0 is equal to C0 minus K0 into T. So there are two shows graph. First will be this is a Cartesian graph. This shows the steady drug loss, that is rate of reaction in constant rate, and this is the uh, logarithm graph. Okay, so this is a C0. Yeah, their rate will be constant. The rate of reaction will be constant. So there will be the steady loss of this drug or reactant. Next point, zero order half-life. So we know what is half-life. The half-life is defined as the time period required for the concentration of drug which decrease to by 1/2. म्हणजे एखाद्या ड्रगचा हाफ क्वांटिटी होण्यासाठी किती वेळ लागतो त्याचे. सो विच टाइम विच इज कॉल्ड ॲज अ हाफ लाईफ. सो हाफ लाईफ or T half or half lifetime is defined as the time period which is required for the concentration of the drug will be decreased to by 1/2. म्हणजे ओरिजिनल कॉन्सन्ट्रेशन पेक्षा हाफ कॉन्सन्ट्रेशन त्याचं कमी होण्यासाठी जेवढा वेळ लागतो which is called as a half life, which is called as a zero order half lifetime or half lifetime of that drug. So equation for this half life, zero order half life, T half is equal to C0 divided by 2K0. C0 will be concentration of the drug. So for example, zero order process, the metabolism, protein binding, enzyme or carrier mediated transport under the saturated condition, and the rate of metabolism, binding or transport of the drug remains constant as its concentration will in this axis of saturation concentration. So zero order example for this, metabolism, protein binding or enzyme or carrier mediated transport under this zero order process. Next will be the administration of drug as a constant rate IV infusion. So this is the example of zero order processes, administration of the drug by with a constant rate by IV infusion. And next example, controlled drug delivery system such as that form IV intramuscular implants or osmotic pumps, which is an example of this zero order process. Next will be the first order kinetics, or which is called as a linear kinetics, and the n will be the 1, that is order of reaction will be the 1. So equation becomes dc by dt is equal to minus kc. So k will be the first order rate constant, which is time inverse or per hour. So what is first order process? So one which rate which is directly proportional to the concentration of the drug which are undergoing reaction, that is greater the concentration, faster will be the reaction. So this in the first order process, if we increase the concentration of the drug, there will be the increase the rate of reaction. So this first order process, one which rate will be directly proportional to the concentration of drug undergoing reaction, that is greater the concentration, faster the reaction. It is because of proportionality between there is a proportionality between the rate of reaction and concentration of drug, that first order says as a linear kinetics. So त्याच्यामुळे काय proportionality maintain राहते. So this first order process, that is rate of reaction and concentration of drug, so they shows linear graph, or they shows linear kinetic. So this equation integrate the above equation, dc by dt minus kc, we get integration of c is equal to integration of c0 minus kt. So the equation becomes c is equal to c0 minus e raised to minus kt, e raised to minus kt. So they are convert this above equation into logarithm form. So log of c is equal to log of c0 minus kt upon 2.303. So first this first order equation, we integrate this equation. So we get, and then after this we convert into this logarithm form. So we get the equation log of C is equal to log of C0 minus Kt upon 2.303. So this first order process is also called as a mono exponential rate process. So this first order process are called as a mono exponential rate process, where first order process, which is characterized by this logarithm or exponential kinetics. So this first order process, which is characterized by logarithmic or exponential kinetics, that is constant fraction of the drug will be undergo reaction per unit time. So why it is called mono exponential rate process, or it is characterized by this logarithm or exponential kinetic? Because every fraction, the constant fraction of the drug will be undergoes reaction per unit time. So this is a first order kinetics, or which is called as a linear kinetics. So continue the next point, that is this shows this first order kinetics shows two types of graph. So first is regular Cartesian plot, and second will be the semi logarithm plot. So this equation T half is equal to, for this half-life equation for this first order rate process, that is T half is equal to 0.693 upon K. So this equation shows that in constant to zero order process, the half-life of first order process is constant. The half-life process of first order process is constant, and it is independent upon initial drug concentration. That is irrespective of what initial drug concentration is time, the time required for the concentration to be decreased by the one of its remains the same. This most pharmacokinetic process, that is absorption, distribution and elimination, which follows first order kinetics. So the half-life equation, that is half-life equation for this first order process, that T half is equal to 0.693 upon K. So this equation shows in constant way to the zero order process. So the half-life of the first order process will be constant, and it is independent upon of the initial drug concentration, that is irrespective of that initial drug concentration. The time required for this concentration to be decreased by the one half of its remain same. So this first order process are absorption, distribution and elimination, and these are the first order process. Next point, pharmacokinetic models. Next point, that is pharmacokinetic model. So what is pharmacokinetic model? So the drug movement within a body, which is complex processes. Therefore, the major objective of this pharmacokinetic model, therefore, develop a generalized and simple approach to describe, analyze and interpret data which is obtained during in vivo and drug deposition studies. So the drug movement, we know that our body, which is very complex. So the major objects from this pharmacokinetic model, that is development of this develop a generalized or simple approach which can describe, analyze or interpret data which are obtained into the in vivo drug deposition study. There are two major approaches in the quantitative study of this various kinetic processes of drug deposition in the body. So in pharmacokinetic models, there are two major approaches, that is first model approach and second model independent approach, which is also called as a compartment analysis. So first approach in the pharmacokinetic model, that is model approach, and second will be the model independent approach, which is also called as a non-compartment analysis. So what is pharmacokinetic model approach? So first, what is model? The model is the hypothesis that employs the mathematical term to the concisely describe quantitative relationship. So what is model? It is a hypothesis which employs the certain mathematical term to the concisely describe the quantitative relationship, which is called as a model. Next term, that is pharmacokinetic model. So it provides concise mean of expressing mathematical or quantitatively or time course of the drug throughout the body. The pharmacokinetic model which provide concise means of expressing mathematically or quantitatively the time course of the drug throughout the body and compute meaningful pharmacokinetic parameter, which is called as a pharmacokinetic model. So there are different methods which is analysis of the pharmacokinetic data. So there are main two types or these approaches. First, model approach, and second will be the model independent approach. In model approach, there are three types. First, compartment model, second physiological model, and distributed model. So in the compartment model, there are mammillary model or Catenary model. Second will be the physiological model, that is perfusion limited model or diffusion limited model, and last will be the distributed parameter model. In model independent approach, the only one model, that is non-compartment analysis. So application of this So next point, that is application of this pharmacokinetic model. So first application, that is characterizing the behavior of the drug in the patient. Second application, predict the concentration of the drug in various body fluid with any dosage regimen. Dosage regimens means the frequency of the drug will be administered or particular dose. Okay, the dosage regimen, it is the frequency of dose will be administered to the particular patient or particular dose, which is called as a dosage regimen. Next application, predict the multiple dose concentration curve for a single dose experiment. Prediction of this multi-dose concentration curve from this single dose experiment. Next application, calculating the optimum dosage regimen. Calculating the optimum dosage regimen for individual patient. Next application, evaluating the risk of toxicity with certain dose regimen. Next application, correlating the plasma concentration with pharmacological response. 7. Evaluating the bioequivalence or bioequivalence between the different formulation of same drug. 8. Application, estimating the possibility of the drug and or the metabolite which are accumulate into the body. 9th application, determine the influence of the altered physiology or disease state on the drug ADME. And last, explaining the drug interaction. So these are the application of this pharmacokinetic model. Next point, these are the models. So first model, that is compartment models. So compartment model, which is also called as a compartment analysis. So compartment analysis is commonly used to estimate the pharmacokinetic characteristics of the drug or character of the drug. So compartment models are several assumptions. The compartment model, which are the several assumptions or compartments, are the first, that is these compartments are the hypothetical in nature. So this compartment model, there are several assumptions. The first assumption, that is the compartments are the hypothetical in nature. The first assumption, the body which is represented as a series of compartments, the body which is represented as a series of compartments, they are arranged either in the series, they are arranged either in the series or parallel to each other and they are communicate reversibly with each other. So first assumption of this compartment analysis, that is body which we represent as a series of compartments, they are connected either series or parallel to each other and they are communicate reversibly with each other. So each compartment, second assumption, each compartment is not real physiologic or anatomic region. So each compartment which is not real physiologic or anatomic region and which is considered as a tissue or group of tissue that have similar drug distribution characteristics. So each compartment which is not real physiological model or real anatomy region, a tissue or a tissue group which are considered as a similar group compartment or which has similar characteristic drug, which has similar drug distribution characteristic. So similar blood flow and their affinity. Third assumption, every organ or tissue or body fluid that can be get equilibrated with drug, which is considered as a separate compartment. So every organ, tissue or body fluid that can be equilibrated with drug and which has considered as a separate compartment. Next assumption, the rate of drug movement between the compartment, that is entry and exit, is described by the first order kinetics. So rate of drug movement, so drug movement from this compartment, which is described by first order kinetics. And last assumption, the rate constant are used to represent the entry and exit from the compartment. These rate constant which are represented, this rate constant which represent the entry and exit from this compartment. So these compartment models are divided into majorly two types: mammillary model and Catenary model. So first, mammillary model. So it consists of one or more peripheral compartments. They are connected to the central compartment. So what is mammillary model? It consists of one or more peripheral compartments which are connected to the central compartment. The central compartment comprises of the plasma or highly perfused tissue. Central compartment mostly comprises plasma or highly perfused tissue such as lungs, liver, kidney, which are rapidly equilibrated with drugs. So they are into the central compartment, and drug will be directly absorbed in this compartment. So in this compartment, drug will be directly absorbed. The elimination occurs from this compartment since the chief organ which is involved in the drug elimination are liver or kidney. So drug will be directly absorbed into this central compartment, and elimination occurs from only those compartments which have chief organ, that is drug elimination, mainly liver and kidney. They are the highly perfused tissue, and therefore they are presumed to be rapidly accessible drug into the systemic circulation. So this liver, kidney, which has highly perfused tissue, so highly perfused means their blood supply will be high, so which has rapidly accessible the drug into the systemic circulation. In peripheral compartment or tissue compartment, they are denoted by the number 2 or 3, and those are low vascularity and their pure perfusion. The peripheral compartment or tissue compartment which are denoted by 2 or 3. The central compartment which is denoted 1, and other compartment from 2 to 3, and those have less vascularity or pure perfusion or less of blood supply. So this is the mammillary. This is the compartment model. This is the model 1 compartment open model IV administration. So intravenous administration. So this one will be the central compartment. So drug will be directly administered into this central compartment, and it will be removed from this. Simply 10 will be the elimination rate constant will be removed from this compartment. Model second, that is by one compartment open model extravascular oral or rectal administration. So first drug will be absorbed, that is K0, 0 to 1, that is central compartment. Then it will be this will be exit from this, that is 1 to 0. Third model will be the 2 compartment open model intravenous administration. So first drug will be the administered into first compartment, then it will be transferred, that is then it will be transferred to second compartment, then it will be transferred central compartment, then it will be transferred to the first compartment, that is central compartment. Then from this compartment it will be excreted or it will be eliminated. So next will be the model 4, that is 2 compartment open model extravascular administration. So first drug will be absorbed. So drug will be absorbed. They are passed into the central compartment. That is first. Then it will be transferred. Then it will be transferred first compartment to second compartment and second compartment to the first compartment, and from the central compartment it will be eliminated. Then fifth model, 3 compartment open model IV administration. So the drug will be first administered into this first compartment, then it will be going to the second compartment, then from the second to first, then then the drug will be transferred from first to third compartment, and then third to one, and direct they eliminated from this first compartment. So this is the model 5. The model 6, 3 compartment open model extravascular administration. So first drug will be administered with the extravascular route, then it will be absorbed into the first compartment, that is 0. There is a less concentration. Then it will be transferred from first compartment, then it will be second compartment to first compartment, then the drug transferred from first to third to first, and it will be eliminated from this first compartment. So these are the compartment model. Next, this is in the compartment mammillary model. Next will be the Catenary model. So in this model, the compartments are joined to another in the series like compartment like train. So in the Catenary model, this model are joined. This model, the compartments are joined one to another in the series like train bogies or compartment. So however is not observable, physiological or anatomical as the various organs are directly linked to the blood compartment. So this model which is rarely used, because in this compartment there is no direct involvement of this physiological anatomical organs they are not linked to the blood compartment. So in this Catenary model, so similar train-like compartment will be these compartments are joined in this Catenary model. So first, the drug will be absorbed from the side. It will be passed from this first compartment. Then it will be transferred first to the second, and it will be transferred first to the second, or this will be transformed first to the third, and from this third it will be transferred to the second to the first, and it will be eliminated from this first compartment. So this is the Catenary model. So there are 2 types, mammillary and the Catenary model. So we stop here. Next point will be study in the next layer. So in this mammillary model, first drug will be direct entered into the compartment and it will be removed. So in the one compartment, the drug will be this is the one compartment. In this 2 compartment, drug will into the first compartment, it goes to the second compartment, and second to the first, and it will be removed from the first element from the first compartment. Next, model number 3 will be the similar, that drug will be entered into the central compartment, then it will be transferred to this peripheral compartments, and then from this peripheral compartment, drug will be entered into the first compartment, and central compartment, it will be excreted or eliminated from this compartment. The mammillary model, the compartments are arranged in the parallel to the central compartment. In Catenary model, drug will be entered into the first compartment, it will be transferred second to the third, and then from this third to the second to the first, and it will be eliminated. They are in Catenary model, the compartments are arranged in the series with central compartments.